In this video, we will be looking at 2D collision detection. What I mean by that is, let's say we have image A, which represents an object on a transparent background, and image B, which represents another object on a transparent background. If we superimpose those two images, will they overlap or not? So basically, that's what I mean by collision detection. All right. So in order to demonstrate this, we will need two visual 2D objects. So I'm going to grab one from the movie file-in operator. This is one that you know about. It's the good old banana. And let's create another one using the circle top. In this case, I'm going to turn on the polygon options and leave it at 3 sides so we get a nice triangle. The banana is already at 1280 by 780 by 720, but the circle, as you probably know, is created by default at a resolution of 256 by 256. So let's just use the parent panel size, which happens to be 1280 by 720, to make both image the same size. This is one of the requirements for this tutorial. Let's make the triangle smaller, actually much smaller. The triangle is the object that will be moving around on screen, and that will be checking to see if it's actually colliding with the banana. Let's make it a nice yellow orange color, something like that. All right. And so the idea is to use a composite to put both images on top of each other. And in this case, we'll use the over operation, just like that. So the plan is for us to move the triangle around on screen using the mouse. And when it's actually overlapping with the banana, we want to know about it. We want to be able to do something. So in order to move it around, I'm going to add a panel chop. Panel provides information about a panel, and by default it uses the parent, and in this case the parent is project 1, so that's perfect. And the information we want to retrieve is the position of the mouse cursor, and this is provided with the inside U and inside V channels. And actually, let's rename this let's rename them to TX and TY, because in a 2D scenario, this is really what they are, translation on X and Y. All right. To actually be able to retrieve those values, because as you can see, if I move my mouse around, it doesn't do anything. The thing is, I'm not currently hovering the project 1 panel, so that's why I'm not getting anything. But if I open a window for project 1, I'm just going to make it much smaller. Let's put it here. So if I move in this window, as you can see, the values in panel 1 actually move. And so the value on the x-axis goes from 0 to 1, from left to right. Since we will be using these values to move the triangle around, we will have to adjust them, because the triangle, as most tops, is anchored in the center of the window, not in the bottom left or bottom or top left. So instead of going from 0 to 1, it actually goes from minus 0.5 to 0.5. So let's just add a math chop to correct this. And we'll go to the range. The from range is already the right one, from 0 to 1, as we saw. But the target range will be minus 0.5 to 0.5. And since we'll be tying that to our circle, we'll just do Alt-N, create a null, And then we're going to be able to assign Tx to center X of our triangle and Ty to center Y. And now if I move around, you can see the triangle is actually moving. It would be better if we could see it here, so let's add a out operator. And now, as you can see, the triangle is just following my mouse. So the idea is to check if the triangle is actually over the banana, and if it is, we will trigger a collision, and perhaps at this stage we can do some more logic. But this tutorial is really just about the collision detection. So how do we do that? It's actually fairly simple. We'll be using the composite operator one more time. This time it won't be used for display purposes. It'll really be only used for the collision detection. So we will connect both the images again, and this time we will leave the operation at multiply. Why? Because multiply basically multiplies the pixel colors in both images, and so when both are transparent or at 0, there's nothing showing up. But as soon as there are two non-transparent pixels, one on top of the other, then we can begin to see something. And this is the result we're getting in the comp2 window. Let me just zoom in. So as you can see, if the triangle is over a transparent area, we get nothing. But if it's over an opaque or at least semi-transparent area, then we get the multiplication of both values. So this is perfect because it lets us know when there's actually a collision. Now, how do we know that for sure? Because visually we can tell that something's happening, but in terms of status, we can actually check that with the analyze top, which has this nice count pixels operation. And so in this case, what it does is really give us the number of overlapping pixels. Or perhaps more precisely, the number. What we want to know is the number of resulting non-transparent pixels. And so to do that, we will select a mask of alpha, because what we care about is the transparency. And so as you can see, as soon as the triangle touches the banana, we get a white result in analyze. This is because even though it's a top, it's actually reporting a number that's a pixel count. And so it's not exactly the most user-friendly way of viewing this data, but as you can guess, if there are currently 100 pixels overlapping, giving a value for R, G, B, and A of 100 is way above 1, so it always yields white. But in our case, it's probably best to just convert that to a chop. So I'll be right-clicking on the output here, going to chop and selecting top to chop. And then we can actually see what I was talking about. So for instance, right now I have 274 overlapping pixels. It's being reported in all the channels, which is kind of weird. But in our case, what we can do is just get rid of the red, the green, the blue. And since the alpha is no longer an alpha value, but really a pixel count, let's just call that, pixels. And so the result we're getting is a number of overlapping pixels, or the number of pixels in the colliding area. All right, so we're almost there. The only thing left is to add a logic chop. And as you know, perhaps, logic will yield a 0 or a 1, a Boolean value. And in this case, we'll be converting the input using off when outside bounds. What this means is we will be setting a minimum and a maximum bound, and when the pixel count is within those bounds, it'll be true. So in our case, the minimum bound really is 1. We just, as long as one pixel is there, then we have a collision. The maximum number of pixels, hard to tell, probably could be very large, but what I'm going to do here is simply use math.inf for infinity. And so anything above 0, or well, anything that's 1 or greater will be triggering a collision. All right, so if we look at this, as soon as I touch the banana, the status here in the logic goes from 0 to 1. All right, so we have our collision detector. Just to make it perhaps visually clear, what I'm going to do is just move this out operator here, and we'll add a background that changes color according to the collision. So let's just add a constant operator here. And let's make it gray, not too dark, but some lighter gray. Obviously, we do not want this thing to be in multiply because we actually want to see it. And we're going to put it under. Whoops. Let's just move this under. Here we are. So the idea is that when there's a collision, we'll be going from alpha 0 to alpha 1, just to showcase visually the collision. And so I'm going to do Alt-N one more time here before linking this value. Oh, you know what? I'd prefer to change the name, because those are really not pixels anymore. They're really just a collision status. So let's add a rename operator, and we'll just call this channel collision from that point on, because it's really what it is. And so we'll link that collision channel to the alpha parameter. And so by default, it'll be black. And as soon as there's collision, it becomes gray. All right, so obviously you could do a lot of things when the collision happens. But the point of this tutorial was to illustrate how this could be done. Now, the fact that we're using in our logic a lower bound of 1 means that as long as 2 non-transparent pixels are overlapping, we have a collision. So in this case, as you can see, it's barely touching. And it might not be exactly what we're going for in terms of collision, because this doesn't really look like it's colliding. So what's nice about using the pixel count is that you can actually move this bounds upwards. So we could say, well, to have an actual collision, I need at least 100 overlapping pixels. So in this case, just barely touching it like before is not enough. I have to go further in to get an actual collision. So this is a nice addition that allows you to tweak the collision to your own needs, which might not be, as we saw, just 1 pixel touching. All right. In order to make that even simpler and to add a few bells and whistles, I created a little component that does 2D collision detection. And I'll just show you how it works. So I'm just going to remove these 6 operators here, because this is basically what we'll be replacing with the component. And I'm going to paste in that component. So this 2D collision detector component pretty much works in the same way. That is, it has 2 inputs, one for each image. So I'm plugging in the triangle in image in the input 1 and the banana in input 2. And it reports its result through 6 channels, the first one being collision. So what this means is that we can actually repair our currently broken network by simply linking the collision value to our alpha value here. Instead of adding a null and linking, I'm just going to use the parameter here, the collision parameter, which is synced to this channel here. And I'm going to assign it to the alpha value of our constant. So in this case, oops, I think there's a little, oh yeah. I'm just going to move it over here. I'll explain in a second. So in this case, we're back to the same result we had before. So basically, as long as one pixel is touching, that's good enough. We have collision. Now, we saw that it was useful to actually, instead of just one pixel, to increase that minimum threshold. So this is what we can do in the component by using minimum overlapping pixels. But where it's perhaps a bit more convenient is using the min A coverage or the min B coverage. What this means is, instead of using an absolute number of pixels, we can actually tell it, well, the triangle must be at least 10% overlapping with the banana, for instance, or 50% or whatever. So the A in this case is the first input and the B is the second input. So in our case, the triangle is connected to the A, or the first input, which is the A. And so we could say, well, let's make it so that the triangle, must be 50% overlapping before a collision is detected. So in this case, what this means is this is not enough. This is not enough. It needs to hit the 50% mark before triggering. And what's interesting about this approach is that it uses a relative value instead of an absolute pixel count, which means that you can change the resolution of the images and not have to worry about figuring out how many pixels the collision should be set for. And the other nice thing is the collision center here. So you may want to position something at the location of the collision. In our case, it's often the position of the arrow, the cursor, but not necessarily. So if I go like this, and I'm just going to bring it back down. If I go like this, I have a collision. But obviously the collision is not happening at the position of the mouse cursor. It's actually happening at the pointy, one of the points of the triangle, or the tip of the banana. And so the center actually reflects that. So if you want to precisely position something where the collision is happening, this is what you can use. And another use of the minimum and minimum coverage is that you can actually set it all the way to 1, which in this case would mean that there would be a collision only when all of the triangle is actually inside the banana. So if you want to check if one object is visually within another one, this would be one way to do it. So if you're interested by this 2D collision detector component, you can get it on my Patreon. The address is provided below in the description. I urge you to subscribe and to like this video if you've enjoyed the content. And I'll see you around in a next video.